wider than that, there's a whole community of people like Cliff who know far more about it than I do. So what I'll try and do is just give you a little overview of some of the things that we've been doing here. I stole Heike's talk as well, which is rather unfortunate. This is what happens if you reply quickly to Jonathan with the title of your talk. You get the pick, and poor Heike had to talk about something else. So I should have given a far better talk, so I apologise on two fronts. So here's the overview. So this is about verification of a certain type of concurrent algorithms. The property that we're verifying is something called linearizability. Do I have a pointer here?
You do this.
This thing. Which was the top one? Oh, wonderful. Okay. So that's fine. Most approaching, most lots of the literature is about sequentially consistent memory, the standard memory model. That's not always realized in practice. So what we're looking at here is what we mean by linearizability on a weak memory model. So this is a different architecture, which is now implemented in some chips. The one that we're looking at, there's a number of different types of weak memory models. The one we're particularly looking at here is this thing called TSO, the total store order. For example, it's implemented in the multi-core architecture that a number of people mentioned earlier. Okay, and the essence of this tiny little bit of contribution that I'm explaining as part of a bigger bit of work is looking at a technique to prove linearizability on TSO, and to do that we need to define what we mean by linearizability on a weak memory model. Okay, and we've got a very simple running example called split lock. So that's, you can now go to sleep if you wish. That's the essence of the talk, and the rest of it is in a bit more detail. Okay, so I'm sure everybody knows far more about this than I do, but just as a recap to set the scene, the model we're looking at is concurrent objects which have shared data. So you've got a number of different processes accessing a bit of shared data. The individual steps of these processes can be interleaved. Okay, and so what we're looking at is then what's the correctness of all this tangled code altogether at a very concrete concurrent level. So we've got multiple operations executed by concurrent processes. We assume a very general client. So here's a little picture down the bottom. Always good to have a picture. You've got three processes, P, Q, and R. They're each doing things. So I've got a Q here. Process P tries to put value on X on a Q, and then it does a DQ. Oh, it gets a Y. Why does it get a Y? Well, in the meantime, process Q has put something on that Q, and it's a shared data structure, so they're manipulating a shared data structure. Okay. Down the bottom, process R is doing some things. Now, because these are a whole bit of code to achieve something, there's a duration to these operations. They're not atomic at these concrete level, and the individual, say an example in a minute, the individual steps can be interleaved. So that's why these things have duration. And what we want to do is look at that, the effect of this thing on the shared data structure, and say, does it make sense? And that version of does it make sense is this idea of linearizability. Okay, so how do we judge this correctness of a concurrent object? Well, we're going to think about histories, and histories are going to record the start and the end of each of these things, that with the invocation and the response. And we're going to assume, although these things have duration, we're going to assume that they take place, the effect of them takes place at some point in the middle, somewhere, of each operation. In this picture, that place where it takes effect is marked by an X. Okay? We're going to call that the linearization point. Okay? And our correctness criteria is going to say, if I do all of these things concurrently, can I untangle them to think of an equivalent, consistent version of the abstract specification, like that, where the linearization points are preserved? So this one, although P starts first of all, it starts an NQ up here. Process R starts a DQ, if its effect takes place earlier than the effect of the P, then that means abstractly you see a DQ first of all before you see the NQ. So although these things have duration, although they overlap, the order of their effects isn't the same as the order of the invocations. It's the order of when in the middle they take effect. Okay? So this is how these concurrent operations might work, and you've got to have a method for checking whether you can untangle something like that into a consistent abstract version. Okay? Now, it's no surprise when you say you're looking at a concrete thing and you're looking to find a consistent abstract version, you're sort of led into the techniques of refinement, which we'll use, because that's about comparing a concurrent thing with an abstract version. So those are the techniques, in fact, we're going to apply here. Okay, so linearizability formally is most common correctness condition in this scenario. We've got this notion of linearization points. Operation calls that don't overlap must take place in their respective order, but if they do overlap, you're allowed to reorder them. And that's best understood by a little picture. So here's my processes, P, Q, and R. They've got operations. From looking at this picture, I know that this X thing here has to take place after anything in grey, because there's no overlap. It has to take place before anything that's blue, because they don't overlap. But things which do overlap, i.e. the other processes in red, could be reordered in an abstract version of that. Okay? That's all. It's a fairly simple concept, well studied, introduced by Haley and Wynne, 1990. Lots of techniques for the verification of this on standard architectures, a whole wealth of work in different forms. So there's all that work. Are we doing anything novel at all here? Well, this is the little question at the bottom. So is spin lock on TSO linearizable with respect to the abstract specification? That's what we're going to try and look at. I've told you what linearizable means. I better do the other part. So that's going to be explain what spin lock is, explain what TSO linearizable is, and give you an abstract version of the specification. And then you'll be able to match it up, hopefully. Okay, so I'll do those things in turn. Firstly, TSO. So TSO it's an architecture, as I said, slightly different from the standard architecture. What does it do? Well, it introduces, conceptually, a little write buffer for each core. So each process, that's these cores, have, instead of reading and writing directly to the shared memory at the bottom, they can read and write to the write buffer, and only later on do the effects of that operation of the write buffer get flushed into the main memory. So it's like a little caching thing. So writes by a process are added to the buffer. Okay, they don't add them to the shared memory, they're only flushed later. Reads are taken from the local buffer unless it's empty. And because to make all of this work, you need this notion of flushes, which are hardware controlled, either hardware controlled, or you can insert, and I'll see an example of this, a little fence instruction in the code to make the CPU flush all of these memories into that. Okay, so this is going to add some delays into the effects of the operation. It's really how to cope with that. So the observable effect of this is it looks like you can get some reordering between reads and writes, because if you're another process reading something from the main memory, the first process might not have written its effect, might not have flushed its effect down. So you can get some reorderings there. And the essential question you have to ask yourself is, when does an operation take effect? And the idea is for other processes, only when that local buffer has been completely flushed. Otherwise, it's not visible to you yet. Okay, so it's a nice little architecture actually used. Here's a little bit of code that runs on that type of architecture. So it's a spin lock. This is just taken from the literature. It's a locking mechanism. There are 3 operations in this: acquire, release, and try acquire. And they're trying to get hold of the lock, which is represented by this number X. So the simple one down here, releases a lock by setting X to 1. So X is 1, the lock is released. Okay. Try acquire tries to get the lock. It makes one attempt. If it's successful, it returns 1, otherwise it fails and turns 0. Acquire, though, spins. That's why it's a spin lock. Okay, and it's, you know, it's, if it gets the lock, that's fine. It locks it. But if another process already has the lock, it will unlock and spin until it gets it. Okay, so here, I think is a code. Okay, so release is very simple, it just sets X equal to 1. Try acquire makes one attempt in this statement to get it, but acquire will loop around until you get it. Okay. So that's the concurrent process, and when these processes are running in parallel, what happens is each individual non-atomic line of this can be interleaved. So one process can start an acquire, another one can come in and start a try acquire. So I'm getting overlapping concurrent operations on some shared memory. And the shared memory here is very simple. One of the bits in this, so slightly confusing in the code is these lock and unlock. That's actually the fences. So these are act as memory barriers and actually lock the code. So acquire and try acquire, they're not delayed because everything's flushed, but the release here doesn't have a memory barrier. So when I set X equal to 1, that's being added to the local buffer of that process. And it's not flushed to the main memory yet. That's the key thing in this. So I've released the lock, I've said it's released, I've put it in my local buffer, and I've gone off and do something else. Only later will a flush come and make that effect visible later on. That's the key bit, and that happens by a flush. So sometimes you've got these unlock here which forces flushes to happen, okay, but sometimes you don't, and that can mess things up. So here's a little run of the code. What happened? Okay, there's not actually much interleaving here. P does an acquire, gets the lock. P does a release, puts it back. Q does a try acquire. Why does it get 0 back rather than 1? Well, the effect of that release, it hasn't been seen yet by the Q because P hasn't flushed. So try acquire thinks it's not released because I haven't flushed down there. Okay, that's the essence of the problem. That's all you really need to know. So what's the abstract specification? Well, that's very simple because I've got to create this condition, so I'm comparing one thing to another. So you have to write down an abstract specification. It's Z style. Essentially very, very simple, and you then say, there's the obvious thing, in fact, we've now got enough to answer that question, and you're thinking, yippee, it's 4:15, we'll go home early, talk's going to be over. Is it linearizable on the abstract specification? Clearly the answer is yes. Oh, it's going to go on for a bit longer here.
Is it going to be on the exam?
I'm afraid so.
Yes, everything's on the exam, especially the minute 28 minutes past. That's a shame of experience of marriage again. A wonderful manner.
You're losing time.
It's all your exam you're losing time for. Mr. Woodcock. It's not linearizable. Something's going wrong. We had this notion of linearizable, and what's gone wrong? Well, let's have a look at this concrete run here. I had that run. What's wrong with that? Should have an abstract counterpart. So let me try those 3 operations in turn in the abstract level. Okay, I'll do an acquire. Let's match up that one. I'll do a release, and then I'll do a try acquire. Well, I did those 3 things in turn in the abstract level, and I get back a 1, whereas up here I got back at 0. Okay, because obviously you need to take account of the local buffers. So if you try and apply a naive definition of linearizability to this TSO architecture, it's not really measuring what we'd like to measure. This is not quite intuitively capturing the notion of correctness that takes account of these buffers. Okay? So the only bit of this work is then to adapt the definition to try and put a bit of TSO intuition back into the correctness condition and then a methodology for verifying it. Okay. So how do you redefine linearizability for TSO? Well, we're not the first people to look at this. At least 2 notable collections of work called TSO linearizability or TSO-SC linearizability, who tackle the problem for different ways. The first one looks at putting local buffers and flushes in the abstract specification. The second one looks at weakening the specification by including some non-determinism to reflect the presence of the buffers. Those are fine. We wanted to investigate a third approach where we didn't change the abstract and concrete specification, but change the definition of linearizability. And we do that by, we have to change something, changing the meaning of when an operation returns. So instead of it just its return point in the code, we think of it as being when it's finally flushed by the CPU. Okay, so the return point of an operation on TSO architecture won't be, in our world, where the operation ceases execution, but can be any point up to the last flush of the variables. Okay, so that's the thing that we're tweaking in this definition. What do you have to do, and you'll be pleased that I'm not going to do all of this in any depth. Formalize the definition, what does it mean, and then provide a proof method. Okay, so there's 2 parts then to the program of work. To formalize the definition, essentially you look at the events and define this adaptation of linearizability by thinking how you can transform histories. And I'll show you on actually this slide, it's easier to understand. So we've got a definition of linearizability that we used to apply. Let's try and still use this, but we're going to just change our histories slightly. So we did that. That's my troublesome example I started with. Now I've just added in invocations and returns of each operation. So P starts an acquire, finishes an acquire. P starts a release, finishes a release. Q starts a try acquire, finishes a try acquire, and then the CPU flushes. Okay. Now if we think of what's the end point of release and say it's not when I do that return there, but when I flush, I'll transform that history into this one here, where the return of the release is now where the flush was. If I make that transformation, and you can actually define this formally, a calculation for that, you start to see that these things overlap. The red and the blue are overlapped. They're concurrent. Okay? Now, with concurrent things, under the normal definition of linearizability, you can reorder them. So I can say, actually, this thing here is equivalent to the following matching sequential history, where I do the try acquire before I do the release. And if I do that, try acquire is returning 0, and that's the right thing because release hasn't happened yet. So if you add in this notion of transforming the histories, you find you're allowed to find a different abstract history to match up. So you have got some consistency, and you can say, yes, spin lock is linearizable on this type of architecture. Okay? And that's the essential endpoint we wanted to get to for this type of definition. Okay? So standard definition, modifying what we think of histories to take into account the TSO nature of the architecture.
Yeah, it could mean any difference between the capital release and the lowercase release stuff. Yeah.
Well, this is the abstract world. I've just capitalized things. I've used different fonts. Okay, so the abstract world has capital there, and this is the concrete world. And I'm trying to match up things in my concrete history with a history I could get from that very simple abstract Z specification. Yeah, and I can find one. Okay, so that's fine. That's a definition. Now, anyone who's done the verifying linearizability will know it's hard on the standard architecture without adding in complications of TSO. Adding in the local buffers adds a whole level of complexity. So one of the things we were interested in doing was trying to find a method where we could split that verification approach in two. And what we're doing here is trying to use an intermediate specification to do that. So instead of doing the verification step in one go, from concrete to abstract, you construct something in the middle, and that splits the verification problem in half, so each is slightly easier. So we're going to use an intermediate specification. I'll just give you a flavour of this. We use an intermediate specification. We split the proof into two steps. One is standard linearizability, and one is actually matching that type of transformation that we had in the definition. And what you do, perhaps best look at this picture, what you do is actually just put local buffers in the abstract specification with a very coarse level of granularity. So down at the bottom here, you've got PQ and CPU. You've got each of these things is the individual step lines in your code. Or while and if and do that. They're all interleaved. Okay, that's very complex. At this intermediate level, I'll add in buffers and therefore flush operations, but I won't interleave them. And if you do that, it seems from the examples we've looked at, you can split this proof into two. The first one just doing with the interleaving bit, and the top one doing with the introduction of the buffers. Okay, it's kind of the obvious idea, and it seems to work out as far as we can tell. So the coarse-grained abstraction is constructed by adding local buffers. You get things like that. So that's the abstract abstract version written in Z, and I've added some buffers in to do the obvious buffer-like things you would expect. It takes a little bit to get this right. And you add a flush operation, and that's the CPU entering all of the buffers. And then you do the standard techniques that we've been working on to try and prove, firstly, the linearizability there, and then secondly, the transformed histories on the bottom there. Okay. Jim's got this look in his eyes, and I think he's going to wave at me shortly, so I won't go in detail in this, but the approach to defining a proof method for linearizability, and this is work with Heiken and Gerhardt, has been to look to adapt notions of non-atomic refinement to try and get a simulation-based method to verify linearizability. And you can adapt that to this context. You need a couple more rules than we had before to cope with flushes and the effect of buffers, but it seems like you can build those in. Okay, so I've just about got to conclusions in the right time. It's about adapting both the definition and the proof method for linearizability for weak memory model. A lot of the work that we've done prior, in particular the work that Gerhard Schellhorn has done on automating and mechanizing the proofs of this in KIV has been enormously valuable, and it should be feasible to automate this proof method here, although we haven't done it yet. And I'll leave it here for further thoughts. It's too long for today.
Okay, so pencils down, stop writing, the end of the examination. So any questions, John? Yes.
As far as I understand, you propose to move the end of an operation to the corresponding flush.
Yeah.
But at that very moment, the same thread can have started, or the same processor can have started another operation already. Doesn't it make the operation of the one process concurrent to itself, to other operations of itself? In a sense?
That further thought encapsulates some of the, yes, there's issues there about this auto-concurrency that you can get and how you deal with that. I mean, those ones about whether you're allowed to reorder them or not.
It's related to the sweep forward.
Yes, so you can come up with a number of different definitions to deal with the situation where you've got one. One says you can't reorder them at all because the original operations weren't reordered, and another says, oh, you can be a bit more relaxed. But yeah, it's good, well spotted.
Okay, anything else? Yes.
So your method, so initially you have your linear ability, this thing, then can your model be compositional?